Hello, good day everyone. Today we shall be looking at physics paper variance 4, physics paper 4 variance 2, May June 2023, Cambridge A level examination, physics paper 4 variance 2. The first question, as you can see, is we are asked to state Newton's law of gravitation. That's the first question. Okay, it's quite straightforward. State Newton's law of gravitation. Okay, there are some keywords in stating this law, so we need to pay attention to. The law states that the force of attraction, between 2-point masses, between 2 point, the force of attraction, this is keyword 2 point, between 2-point masses is directly proportional to the product of the masses. Is directly proportional to the product of the masses. Is directly proportional to the product of the masses, and inversely proportional to the square of the distance, apart. That's the law, Newton laws of gravitation. The keywords there: 2-point masses, force of attraction between 2-point masses, directly proportional to the product of the masses, and inversely proportional to the square of the distance. Next one. A satellite is in circular orbit around a planet. So radius of the orbit is r, and period of the orbit is t. The planet is a uniform sphere. Use Newton's law of gravitation to show that r and t are related by this. Now, let me draw something. Let's say this is the planet or the Earth. There's a satellite orbiting it. This is a satellite orbiting this planet. And the question said that the radius of the orbit is r. Remember that from here, from center to edge, will be the radius of this Earth. From center of this Earth to center of this satellite will be big R. Distance between this planet and the satellite. This is the satellite. So the distance between the Earth, the planet, and the satellite, center to center, is R. So the satellite is orbiting this planet. So we are asked to show that this, using the laws of gravitation to show that these relationships are related. At least from this question, we have two bodies interacting, the satellite and the planet. So there will be force of attraction when two bodies are interacting. According to Newton's law, the force of attraction between them will be G, mass of the satellite, and the other mass, all over distance between them, that's R squared. Now, since the satellite is orbiting the planet in a circular path, the force of attraction will provide centripetal force, Fc. Force of attraction will provide centripetal force. What is centripetal force? The force that made the satellite tend toward the center. It will rotate in such a way that the body tend toward the center. So the force of attraction provides that. And what's the force of attraction? GMSM all over R squared. What's the centripetal force? The centripetal force, the formula for centripetal force is the centripetal force in this case, it is a satellite that is in a circular orbit. It will be mRW squared or mv squared. But in this case, what is orbiting is the satellite. So the mass is mass of the satellite. So at the end of the day, we have the mass of satellite cancel mass of satellite. So what do you have here? We have Gm over R squared equal to R. W is angular frequency, which is 2 pi over T. There's the square. So from here, we have Gm over R squared equal R times 4 pi squared over T squared. By the time you cross multiply, what do you have? T squared Gm equal to R cubed 4 pi squared. When you cross multiply, this is the relationship that asks us to show. So let me write it. So 4 pi squared R cubed is equal to Gm T squared. That's the relationship. Yeah. Next question. The Earth may be considered to be uniform sphere. Now the uniform sphere we are talking about, the planet is uniform sphere. So we are considering it to be the Earth, the planet they are talking about. So this at the center is the Earth. So the mass of the Earth is 5.98 times 10 to the power 24 kg. And the radius, this radius is 6.37 times 10 to the power 6. A geostationary satellite is in orbit around the Earth. So what is revolving around the Earth, as we said earlier, is a geostationary satellite. Use the expression to determine the height of the satellite above the Earth's surface. Let me redraw the diagram again. let me draw the diagram again. This is the Earth. From here to here, center to edge, is the radius of the Earth. This is the one orbiting the Earth, the geostationary object. The distance between this object and the Earth is big R. So what they are looking for is the height above the surface of the Earth. This is the height above the surface of the Earth. The height, let me draw it again so it will look a bit neat. Maybe I'll use two colors so you can differentiate the Earth and what is orbiting it. Okay. Now, this is the Earth. From here to here, from center to edge, is the radius of the Earth. Now, there's a satellite orbiting the Earth. There's a satellite orbiting the Earth. Now, this is satellite orbiting the Earth. The distance between that satellite and the Earth is big R. So the question asks us to find the height above the surface of the Earth. This is the surface of the Earth. It said the height of the satellite. From the satellite to the surface of the Earth. That is the height. That's what we are looking for. Like we said earlier, the interaction between, and one thing about geostationary satellite is that a geostationary satellite revolves around the Earth for 24 hours. So the period will be 24 hours. It revolves 24 hours. That's one thing about geostationary object. So from here, and we are given the mass of the satellite to be this, and the radius is 6.37 times 10 to the power 7. So from here, from the previous relationship we had before, we have already proven the relationship between them to be this. Now, first, we are looking for the height. But first, let's look for the distance between them, r. So let me make r cubed the subject of formula. So it will be t squared. If I make r cubed the subject of formula to be t squared gm all over 4 pi squared. So r cubed will be, what's t? 24 hours. All square multiplied by, what's g? Let me make it like this. Okay, so we have r cubed t squared is 24 hours. 1 hour, we have to convert it to second. is 60 minutes. 60 minutes, so 60 times 60 all square multiplied by g. G is 6.67 times 10 to the power minus 11 multiplied by the mass. The mass is 5.98 times 10 to the power 24 divided by 4 pi squared. At the end of the day, R cube, let's put it into a calculator. So R cube will be, when you input this in the calculator, we're going to have 7.54 7.5421 times 10 to the power 22. So R will now be cube root of 7.54 times 10 to the power 22. So our R will be 4.22 times 10 to the power 7. That's the distance between them. But the question asks us to find the height. The question asks us to find the height above the height of the satellite above the Earth. When you check the diagram here, you see that the distance between them equal to the height plus radius of the Earth. Check this. The height plus radius of the Earth will give us big R. So height, to find the height, it will be radius, distance between them minus radius of the Earth. So therefore our height will now be, what's the distance between them? 4.22 times 10 to the power 7. Radius of the Earth, we given the question, 6.37 times 10 to the power 6. 6.37, 4.22. So when you subtract it, so the height will give us 3.58 times 10 to the power 7. That's the answer. That's the height above the height of the satellite above the Earth's surface. The next question. Another satellite is in circular orbit around the Earth. Now, we have another satellite around the Earth with the same radius, the same period, which means the satellite is also rotating the Earth for 24 hours with the same radius. The same radius distance between them, between the Earth and that satellite, is the same as the first one. Calculate the angular speed. You have to calculate what? Angular speed. Okay. What's the formula for angular speed? The angular speed is 2 pi over period. Since the same period, that's 24 hours, 2 pi over 24 hours. And you guys know that 24 hours is 24 converted to seconds, 24 times 60 to 60. So angular speed will give us 7.3 times 10 to the power minus 5. That's the angular speed. 7.3 times 10 to the power minus 5. The unit for angular speed is radian per second. That's it. Now, despite having the next question, despite having the same orbital period, the orbit of this satellite is not geostationary, which means that the reason why this orbit might not be geostationary is that maybe it's not at the particular height above the surface of the Earth. That's the most likely the reason why it's not a geostationary object. Suggest two ways in which the orbit of this satellite could be different from the orbit Okay. Now they're just trying to tell us that we should suggest two ways why the orbit is not geostationary. Why the other one, the previous question, is in geostationary. But the simple way is just to inverse the property of geostationary. You know, geostationary orbit rotates from west to east. That's one of the properties of geostationary orbit. They rotate from west to east. Since this is not geostationary, which means it rotates opposite of it. So which means this orbit rotate from east to west. That is it. We negate the property of geostationary. Geostationary is from west to east. So this one will be east to west for 24 hours. You know that geostationary orbit must be about a particular height above the earth. Do you get? Geostationary objects must be about 3.6 times 10 per 7 meter above the earth. So which means this one is not definitely, this one is definitely not 3.6 times 10 per 7 meter above the earth. That is, you just negate the property of geostationary orbit. That's all. Or geostationary orbit is always the access for two. I'm just trying to add one more. Geostationary orbit is usually stationed above the equator. So this one is definitely not above the equator. So the orbit, this orbit satellite is not, probably let's say equatorial, not above the equator. So that's just what they're trying to ask us. They asked us for two, just provide three for your bonus. The next question says state what is meant by an ideal gas. Okay. Once they ask this question, what they expect us to say, ideal that a gas that obeys ideal gas equation. A gas that obeys ideal gas equation, PV proportional to absolute temperature. This is what is called ideal gas. A gas that obeys ideal gas equation, PV proportional to all temperature. But you must tell them the value of you must tell them the meaning of PV and T for all values of pressure, which is P, volume for all value, which is V, and absolute or thermodynamic temperature, T. You have to tell them the meaning of all the values you put on the equation. That's it. A gas that obeys the ideal gas equation, which is PV proportional to temperature, for all value of pressure, volume, and absolute temperature. That's it. State the temperature in degrees Celsius as absolute zero. Now, this is a topic. I'm still going to treat all this topic topically after solving the past papers. So for you to understand all the concept, absolute zero is minus 273.15 degrees Celsius. I'll divide absolute zero. A sealed vessel contains mass. A sealed vessel contains mass. The mass is this, as you can see, of an ideal gas. This is the temperature. You have to convert it to Kelvin. The pressure of the gas is this, and the volume of the gas is this. Calculate the number of moles. Calculate the number of, this number of moles, this number of molecules is key. Number of molecules is capital letter N. Number of moles is small letter n. So in this case, we are going to use PV. We can use any one of them. PV equal to NKT, or you can use any of them. I'll use them so you see how to mix it of them. Or PV equal to nRT. PV equal to NKT look straightforward. So you are looking for number of molecules, capital letter N. That's PV over KT. So that will be, what's P? We have a P 1.37 times 10 raised to the power 5. The volume is 0.64 meter cube over K, Boltzmann constant. To check the front page is 1.38 times 10 raised to the power minus 23 multiplied by temperature 227 degrees Celsius. Convert it to Kelvin. 227 plus 273. That will give you 500. When you put this in your calculator, your number of molecules will give us 1.27 times 10 raised to the power 25. That's number of molecules. Now, if I want to use the other equation, first, let me find the number of mole first. Number of mole, if we make small n the subway formula, is PV over RT. So number of mole, what's my P? 1.37 times 10 raised to the power 5. My volume 0.640 over R is molar gas constant. A molar gas constant is also in the front page. The value is 8.31. Absolute temperature 227 plus 273, 500. In this case, my number of mole, when you put in your calc, it give you 21.1023. Now, but we are not looking for number of mole, we are looking for number of molecules. The relationship that relates number of mole and number of molecules. Number of mole is number of molecules over Avogadro's number. So, and I'm looking for number of molecule N to be NNA. So number of molecule with number of mole is 21.1023. Avogadro's number is 6.02 times 10 to the power 23 on the front page. So when you multiply this together, it also gives us 1.27 times 10 to the power 25. These are the two ways to solve the question and how to use the formula. The next one is mass of one molecule. Mass of one molecule. Now, for all the molecules, I think we are given a mass 0.0424. For all the molecules, 0.00424 grams. for all the molecules, that's a kilogram, we have 1.27 times 10 to the power 25. Now, for all the molecules, it says you should find the mass of one molecule. So for one molecule, I don't know the mass x. So cross multiply. That will be 1.27 times 10 to the power 25 x equal to 0.00424 times 1. So x will be 0.00424 divided by 1.27 times 10 to the power 25. So mass of one molecule will give us 3.34 times 10 raised to the power minus 27. That is it. Now the last part of the question. No, okay, you still have two more questions on this part. It said the root mean square speed of the gas molecule. We are looking for the root mean square speed. Okay, the root mean square speed of the gas molecule. Now in this question, to calculate the root mean square speed of this molecule, I can also solve it. Let's see, we can have two ways. Let's say a formula that involves root mean square. Let's go back to the front page. The front page. Probably not given. The front page. Okay. I'm very sure you're familiar with this formula. Very sure you're familiar with this formula. PV equal to equation of kinetic theory model of ideal gas. PV equal to N small m mean square speed. So I'm very sure you're familiar with this. So where the Nm in that equation, the Nm is the mass of the gas. I explain this better. I explain it and analyze it in one of my topical video will be posted soon. What we are looking for is the mean square speed. So let's make the mean square speed the subject formula. That will be 3PV equal to Nm mean square speed. So in this case, the mean square speed is 3PV over Nm. So mean square will be 3. For the pressure, okay, in this case, what's our pressure? I think we given before in the question, 1.37 times 10 to the power 5. The volume is 0.640, the volume, all over Nm, which I said is the mass of the gas. Mass of the gas is 0.0424 at the end of the day. So when you take the square root of both, the square root of this, square root cancels square. So the speed, put it in a calc, will give us 2490 meter per second. That's the speed. Alternatively, kinetic energy of a gas molecule, can be 3 over 2 kT. And what's formula for kinetic energy? Half mv squared. Half mv squared. In this case, these are v, the mean square speed, equal to 3 over 2 kT, right? The same thing. Half cancel half. So I can find the mean square speed to be 3 kT over mass. So the mean square speed is 3 kT over mass. That's 3 multiplied by K. K is Boltzmann constant, 1.38 times 10 to the power, I think 23, multiplied by temperature. Temperature is 500, divided by mass. In this case, this mass is mass of one molecule, because you are discussing about kinetic energy of one molecule. This one is the formula is about kinetic energy of one molecule of gas. So mass is mass of one molecule, which is 3.34 times 10 to the power minus 27. So when you find the square root of this, it also gives us 2490. So the speed is 2490 meters per second when you approximate it. I believe you understand. The next question. Now the gas in V is now cooled gradually to absolute zero. So I'll sketch the variation with thermodynamic temperature T, or root mean square speed of the gas molecule against this. Now, I just make use of a formula right now that the formula is kinetic energy equal to 3 over 2 kT of a gas molecule, which I now said half mc squared equal to 3 over 2 kT. So half cancel half. So I have mc squared equal to 3 kT. So I want to make V squared the substitute formula. That's 3 kT over mass. So V is square root of 3 kT over mass. What I'm trying to do is that the relationship between speed, which means square speed, and temperature is that they are directly proportional to each other. Speed is directly proportional to the square root of temperature, which can be V squared proportional to T. Don't forget, this my V squared, the root mean square speed is still something like this. So V squared is proportional to T. So I'm plotting a graph of V against T. And they said the gas is now cooled gradually to absolute zero. So now it's going to be the gas is now cooled gradually. Now the graph will look like this, it's a parabolic, going to give us a parabolic nature. Why? It's because of the power on the speed. It's parabola, as in it's quadratic. So when you have two quantities that proportional to each other, it's supposed to be straight. But in this case, it's not going to be straight. It's going to be a parabolic nature. And again, they said it's gradually cooled. The gas is cooled. When a gas is gradually cooled, the speed will be decreasing, but a positive gradient. It's cooled. Just imagine hot water. When it's hot, the molecule will be vibrating. When it's cool, they gradually lose their energy and be calming down gradually. So which means that the speed will be decreasing. Now, for a decreasing velocity and parabolic nature is going to be like this. This is a decreasing this thing to stop at, according to the question, 500 to a certain value of v. This is a graph. It's curved because it's a parabolic graph. It has a power of 2, quadratic. So that's it. Number 3 question. State the first law of thermodynamics. State the first law of what? Thermodynamics. Okay, let's quickly look at it. The first law of thermodynamics states that the increase in internal energy, the increase in internal energy of a system, the increase in internal energy of a system is equal to the sum of energy by heating, is equal to the sum of energy by heating, that's heat energy Q, and work done on a system, that's W. Internal energy symbol is U. I make the word increase, that's change in U. This is first law of thermodynamics. The increase in internal energy of a system is equal to the sum of energy by heating Q and work done on the system W. So which means it's like this. This equal to Q plus W. I already said the meaning from the law. That's it. Remember that it's key for us to know that plus W is work done on a system, plus W is work done. Work is very important. Work done on a system. Q is heat energy added to the system, plus Q heat transfer is heat transfer to the system, heat transfer or added to the system. It's key to understand this key. It turned to minus W if work is done by the system, it will be minus W. If it is removed from the system, plus Q turned to minus Q. It's key to understand this concept. Now, the state of an ideal gas is continuously changed according to the cycle A, B, C, D, A, from A back to A. That's a loop. You should take note of that. Shown. Complete the table by placing a tick. Now, from A to B, what's going on there? When you check from A to B, the pressure is the same, but the volume is decreasing. It's coming toward the left. Volume decreases. From A to B, volume decreases. Check the arrow. It's coming from right to left. Volume decreases at constant pressure. Volume decreases at constant pressure. Now the pressure is constant. And when the first is that the volume decreases. Since the volume is decreasing, work is done not by the system, on the system. Since volume decreases, work is done on the system. If it's expanding, work is done by the system. If volume is decreasing, work is done on the system. So when work is done on the system, it means, so in that case, from A to B, we say the work done is positive because work is done on the system. What about change in internal energy? Now, since work done is positive, don't be confused and don't let that one confuse you. Let's see what will happen to internal energy. Oh, great. Remember that the volume is decreasing. As the volume is decreasing, internal energy can also be kinetic. Is the sum of random kinetic and potential energy, internal energy. Since volume is decreasing at constant pressure, which means constant pressure, constant temperature, kinetic energy will be minimum or zero. At the same time, since volume is decreasing, the space are also decreasing. So which means this is also potential energy is also decreasing. So with what is happening, internal energy is also decreasing. That's the key. B to C. Let's check it. Here's B to C. Oh, let me erase this. Look at B to C from the screen. When you check B to C, pressure is increasing. Pressure is what? Increasing. And pressure, okay, let me label it back so you guys will know. B to C, pressure increase, so temperature will also increase because pressure is proportional to temperature. So kinetic energy will also increase from B to C. So we can say that internal energy in this case will increase because kinetic energy is increasing, temperature will increase. And so we can say internal energy in this case will increase. Let's see B to C, internal energy is increasing. Let's see the work done. What is happening to the work done in this case from B to C? Oh, it happened at a constant volume. Check it. B to C at a constant volume. Work done is PdV. Since it happened at a constant volume, change in volume will be zero. In that case, work done is zero. In this case, work done is zero. That's it. From on figure 2 of the same question, use the first law of thermodynamics to describe and explain the energy transfer associated with one complete cycle, like I said, loop A back to A. Now, there's something about cycle. About cycle, once the internal energy about a cycle process like this A, B, C, D, A is that the change in internal energy of A, B, C, D, A, the change in internal energy of A, B, C, D, A, I mean internal energy from A to B plus internal energy B to C plus internal energy of C to D plus internal energy of D to A must be 0. That's number one. It must be 0. And at the same time, at the same time, more work. When you check this, this is a normal. This one in a loop. In first law in thermodynamics, the internal energy in a loop is always equal to 0. That's what I just put down here. When you check the diagram, you'll see that CD is at higher part than AB. And when you check CD, the work done, the volume is increasing. AB, volume is decreasing when you check it. This one is X. C to D, volume increase. A to B, volume decreasing. I can also say that more work is done. Okay, let me put it like this. More work is done in CD than AB. Come on. If you check this again, DA and CB, they have constant volume, but the pressure changes. At constant volume, volume is 0, so no work is done. So no work is done. You have to analyze it like that. No work is done. No work is done on BC and DA. So overall gas does work. I think this is what they want us to talk about. Overall gas does work. Okay, this is all I'll just talk about. Number 4 question. A small steel sphere is oscillating vertically on the end of a spring as shown in figure 4.1. This is vertical oscillation, up and down, up and down, okay, up and down from equilibrium position. X is 0, it's moved up to gain, it moved up, it shrink, it also moved down. In both cases, this vertical oscillation, this equilibrium position, in both cases, this is 0. There will be a small distance here, and also down, there's another distance down. If you measure from 0 to up, there will be distance down to up. down from 0 to down to. So in both cases, let me call this is up and down. As you can see, in both cases, it's both gaining potential energy. One is opposite of the other. That is just it. Okay, I'm coming back to that. The velocity v of a sphere varies with displacement from equilibrium position. That it varies, like I said, when x is 0 from to the. According to this equation, x is in centimeter. Calculate the frequency. Okay, this equation or this model is of this format. This is the real formula they use in forming it. V equal to plus or minus W square root A square minus S square. W is the angular velocity, A is amplitude, X is the displacement. So when you check it, this 9.7 is taking position of W. So we can say W angular velocity is 9.7, but we have to find frequency. W is 2 pi f equal to 9.7. So frequency is 9.7 over 2 pi. Use your calculator as 9.7 over 2 pi. We have 1.54. That's it. The next one, show that the amplitude is 3.4. When you check it, 11.6 is taking position of A. So I can say A squared is equal to 11.6. A equal to square root of 11.6. That's 3.4 centimeter. Calculate the maximum acceleration. Simple harmonic motion. Acceleration in simple harmonic motion is minus W square x. But maximum acceleration is minus W square a. So maximum acceleration is already we have our omega W. Do we have it? Yes, to be 9.7. Our omega is 9.7 squared, while our amplitude is 3.41 centimeter. So take it to meter, 3.4 divided by 100. So our acceleration is 9.7 squared multiplied by 3.4 divided by 100. 3.4 divided by 100. So we have 0.034. So the maximum acceleration is 3.2 meters per second squared. Now we are asked to sketch the graph of acceleration. Now, okay, don't also be confused. Simple harmonic motion states that A is minus W square x, not 2A. And the graph for simple harmonic motion graph is always negative gradient like this. So this place here is amplitude. When you trace this down, here will be acceleration. So now our amplitude here is 3.41. Let's trace 3.41 here on the x-axis. 3.4 from here. Each line is 0.2. 1, 2, 3. Let me zoom it so you can see it. Oh, sorry. let me zoom it. Each line is 0.2. 1, 2, 3, 4, 5, 6, 7. This 3.4, 3.6, 3.8. Yeah, this 3.4. So this side too will be 7 line. 1, 2, 3, 4, 5, 6, 7. Is the opposite of it. So you draw, so which means it will be here with acceleration. To also be here with acceleration. So you draw a straight line that passes to the origin. Yes, this is the graph. So this side, this is y is a, x is minus 3.4. So the same thing here, the same thing here. Sorry, x and y. Sorry. The coordinate is x first. What's x? 3.4. 3.4 and a. So here is minus. This is minus 3.4. This is minus 3.4. This one. Minus 3.4. X axis, y is a. This one is plus 3.4. This is the opposite of it. That's the graph. That's what the examiner wants to see. Now, next question. Now, the next question is describe without calculation the interchange between potential energy and kinetic energy of oscillation. The interchange between potential and kinetic energy. Let me go back to this question. Check this. Like I said, it's going up and down. It's the same thing as the oscillation is similar to this. When it displaces this bulb, it goes up, it gains height. It comes back and also go to this side. It also gains height. This is probably down from here. This is the equilibrium position when x is 0. This is up, like this. At this point here, it has gained potential energy at this point, but because there is height. At that point, the potential energy is maximum, no kinetic energy. At this point too, potential energy is maximum, no kinetic. At maximum height, velocity is 0, no kinetic. At the equilibrium position, kinetic energy is maximum, potential energy is 0. That's what is happening. Up we have this side we have maximum kinetic energy, maximum potential energy, no kinetic. The same thing with down here. It has gained height, maximum potential, no kinetic. But at the middle equilibrium position, x is 0, no potential, but there is kinetic. is maximum. That's what is happening. So when you move up, kinetic energy is being converted to potential energy. When you move down to kinetic energy is being converted to what? Potential energy. U is up, D is down, M is the middle. Kinetic energy is maximum at that point. What's potential energy anyway? Potential energy in a spring is half kx squared. Kinetic energy is half mv squared. Now let's go back. I've shown you some key. Up is potential energy, that's half kx squared. You know, in a spring, K is mw squared. So in a spring, K is mw squared. So potential energy will be half mw squared x. You know, it's maximum at that point. The potential energy is maximum. Let me use the right word. So let me make it like this. When the spring moves up, potential energy is maximum. So potential energy will now be half k. K is what? mw squared. At maximum, x will turn to a. X is equal to a when it's maximum, equal to amplitude. At the same time, at the middle, that's m, or equilibrium position. At the middle or equilibrium position, kinetic energy is maximum. Kinetic energy is half mv squared. So at that point, half m, v is rw. So kinetic energy, which is maximum, you know, half m, instead of writing r, of course it's maximum, it will be a, half a squared w squared. Oh, this one too is squared. So you can see at every point, at the middle, what's kinetic energy? Half maw squared. When you move up or down, potential energy is what? Half m squared, half mw squared, a squared. So at every point of oscillating, the energy, the total energy is constant. That's the key. At every point of oscillation. So this is it. How do I put it? Okay. The total energy at every point in terms of energy at every point, the total energy at every point is constant, equal to half m a squared w squared. Is 3 marks, 3 first point, comma, at equilibrium position. You have to tell them what we noticed. At equilibrium position, kinetic energy is maximum. Why? Potential energy is 0. At a displacement, or let me put it like this. Don't put it like this. Okay. At a point higher than equilibrium position, you know, at a point higher than equilibrium position, potential energy at a point higher than equilibrium position or maximum displacement. Okay, yeah, or maximum displacement. Potential energy at that point is maximum. Why? Kinetic energy at that point is zero. This is what the question wants to talk about. Question 5. Two capacitors A and B are connected into the circuit. Yeah, the circuit is as shown. So the capacitor A has a capacitance C. A has a capacitance of C. Capacitor B has a capacitance of 3C. The electromotive force of the cell is V. Okay, this is the voltage on equal lengths of line with voltage or EMF. So the two-way switch S, you can see the switch is initially positioned at position X. Okay, and capacitor B is on charge. When you see this question, you see that C is currently charging and B has no charge at all, according to this diagram. State in terms of V and C expression for initial charge A. That the charge A means the charge on capacitance C. So the charge on capacitance C will be CV. So Q equal to CV. So capacitance at A is C multiplied by voltage. That's it. The next one, the initial energy stored in capacitor A. Okay, the initial energy stored in capacitor A. What's the formula for energy stored? Half CV squared. Capacitor A, the capacitor is C, the voltage is V squared. Now, two-way switch is now moved to Y. What do you think is happening? They now move this switch is now at Y. When they move it to Y, A and B are now connected. Remember that A has been charged. What do you think will happen? Which means that A will discharge, but there's no voltage connected in this case. What they connect together is capacitor A and B together. No voltage, which means literally A is charging B. So now A will be discharging while B will be what? Charging until the charges are equal. It's like thermal equilibrium. Until the charges are the same before B starts charging. Until A doesn't have more than B anymore. As it is right now, the charge of A right now in this connection, with this connection, the charge of A is greater than the charge of B. So when it's fully charged, QA, charge at A will equal to charge at B when it's fully charged. This is what the question is trying to tell us. State and explain what happened to the charge that was initially on the plate of capacitor A. Oh, that's exactly what they're trying to tell us. Is it some of the charges in capacitor A will be transferred to capacitor B. It's like capacitor A charging capacitor B. The process stops when the charge in B is equal to charges. The process stops when the charges in B is equal to the charges in A. That's what the question is asking us. Now, we must show that the final potential difference in B is given as that. The total charge, these are two capacitors in parallel. The voltage across A will be equal to voltage across B. This is condition for parallel capacitors. The voltage are the same thing. So I remember that charge at A plus charge at B will give us the total charge. What's the charge at A? CV. What's the charge at B? The formula for charge is CV. At B, capacitor at B is 3C. They get let me put voltage at A, voltage at B equal to total charge. That will be the total capacitor times total voltage. Remember that the voltage are the same since they're in parallel. So I can say VA is the same thing as VB, right? VA is the same thing as VB equal to CV. This one gives me 4C VB equal to CV. C cancel what? C. So the voltage across B is V over 4. That's what the question is trying to ask us to do. The next question. Determine an expression in terms of V and C for the decrease in total energy that is stored in the capacitor as a result of change in position. Yes, there will be decrease in total energy. There will be decrease in total energy as a result of what? Change in position of the switch. Energy will decrease. Okay, energy stored in the capacitor. Oh, sorry, I didn't write it there. Energy stored in the capacitor is half CV squared. Energy stored in the capacitor is half CV squared. Now, there will be decrease. Initially, the energy stored in A is half CV squared. It will decrease to half something, which I don't know. It will decrease to half something, which I don't know. Now, that's what we're looking for. Now, energy stored in A is half CV squared. What's the energy stored in B? Half C. C in B is 3C. The voltage in B will be, okay, the voltage, or let's look at it like this. Let's look at it in this way. Determine the expression in terms of the decrease in total energy. Okay, when C is now charging, when A is now charging B, when A is charging B, at that point, the total capacitance at that point, or total capacitor at that point is C plus 3C, that's 4C. At that point, energy stored will be half C, in this case is 4C. At that point, the voltage is V over 4, all squared. So energy stored will be 2C, 2 here 1, 2 here 2, 2C multiplied by V squared over 4. That will be 2 here 1, 2 here 2. That will be, no, this one is 16. 4 square is 16. 4 square is 16. So in that case, we have in that case we have 2C multiplied by V squared over 2 here 1, 2 here 2. This is 4. 4 square is 16. So we have 2 here 1, 2 here is 8. We have 1 over 8 CV squared. 1 over 8 CV squared. So this is the energy stored. This is the energy during the charging process, 1 over 8 CV squared. So decrease in energy is half CV squared minus 1 over 8 CV squared. So which will give us LCM 8 CV squared minus 2 CV squared over 16. That gives us 6 CV squared over 16, 3 over 8. 3 over 8 CV squared. That will be the answer. Number 6. A heavy aluminium disc has a radius of 0.36. It has a radius of 0.36. Okay, aluminium disc. The disc rotates with wheels of a vehicle and form the disc rotates with the wheel of the vehicle. Okay, and form part of electromagnetic braking system on the vehicle. In order to activate the braking system, a uniform magnetic field, okay, of flux density B, this is our flux density 0.17 Tesla, is switched on. The magnetic field is perpendicular to the plane of rotation of the disc. Define magnetic flux. That's the first question. Okay, magnetic flux, if you've forgotten, the symbol is phi, like this. That's magnetic flux. It's the product of magnetic flux density. It's a product of magnetic flux density B and perpendicular area A, perpendicular area A to the magnetic field, the magnetic field. That's it. So the formula is magnetic flux equal to B times A. I've explained the definition, the meaning from definition. This is magnetic flux, flux density, and area. You get 2 marks. Next question. Calculate the magnetic flux through the disks. What's the formula for magnetic flux? Like I said, magnetic flux density multiplied by what? Area. So in this case, area is pi r squared. So area is pi r squared. So magnetic flux in this case will be magnetic flux density is 0.17 multiplied by pi. What's radius? 0.36 squared. Punch it to your calculator. What do you have? 6.9 times 10 to the minus 2. The unit of magnetic flux is Weber, WB. Next question. Now the disc is rotating at the rate of 25 revolutions per second. It's like number of revolutions over time. This is like the frequency. This is frequency. If it's rotating, okay, that EMF is induced because it's now rotating. That's Faraday's law. Faraday's law is state that the induced EMF is proportional to the rate of change of magnetic flux. The induced EMF is proportional to the rate of magnetic flux. So, which means that a magnetic flux, like I said earlier, is B times area all over time, which can be B times area over 1 over time. So in this case, 1 over time is frequency. 1 over period is frequency. So this formula can be B times area. 1 over time is frequency. So we can use BAF. That is it for induced EMF. So induced EMF, what's my B? My B is what do you have? B, magnetic field, magnetic flux density. Where is it? Let's check it. Already we have our magnetic flux. That's B times area, 6.9. Okay, BA is magnetic flux multiplied by frequency. And our frequency from previous question is 0.069. So sorry, magnetic flux. And frequency is 25. When you multiply it together, all you have 1.7. Simple. That's it. And the next question. The axial and the rim are connected to an external circuit. The axial and the rim, okay, they are connected. Let me check it. This axial and the rim are connected to an external circuit. Okay, that enable the energy of the rotation. That enable the energy of the rotation of the disc to be stored for future use. The direction of rotation is shown in Figure 6.1. Use Lenz's law of electromagnetic induction to determine whether the current in the disc is from the rim to the axis or from the axis to the rim. Explain your reason. Now there's something they said that enable the energy of rotation of the disc. which means the disc is rotating. Let's check it. The axis is helping, the disc is rotating. Can you see the direction? You can see the magnetic field. See the direction, which means here is north, here is south. Look at it. So the disc is rotating the magnetic field. Remember what happened when there is motion in the magnetic field? EMF is induced. You get? EMF is induced, which thus bring about induced current in the ring because the ring is rotating. So due to the fact that the axle is connected to the ring, current flow from the ring to the axle, and the axle is also induced with a current. Now that this current is flowing in the axle, are you following me now? The axle set up its own magnetic field according to Lenz's law. It set up this magnetic field so as to oppose the motion that produced it initially. Which motion produced it? That's the ring. At the end of the day, I conclude that current flow from ring to axle. I get all my full point. Let me put it down. Please take note of what I said. I might not be able to remember everything when I'm writing down. Now, due to continuous motion, or due to continuous motion of the ring in a magnetic field, comma, EMF is induced in the ring, which thus brings about induced current, since the axle is connected to the ring. Current is also induced in the axle by the ring. According to Fleming's left-hand rule, according to Fleming's left-hand rule, the axle set up its own magnetic field, which tend to oppose the motion of force that produces it initially. Hence, current flow from ring to axle. That is it. I believe it's detailed enough for you to understand it. Number 7. Oh, bridge wave rectifier. Let's see it. 4 diodes. That's how I know it's bridge wave. You have 4 diodes. 4 diodes in a bridge rectifier circuit to produce rectification of a sinusoidal AC input. Figure 7.1 show part of the circuit, but 3 diodes are missing. Okay, this is another aspect of it. Look at the way they even put it. The PD across the load is this, blah blah blah. State the name of the type of rectification produced, since it's a bridge rectifier. So, and it's 4. It's called full wave rectification. Full wave rectification. Full wave rectification is when it involves 4 diodes. Complete 7.1 by drawing the 3 missing diodes. Okay. This they want to test how you know how. They want to test if you know how the current flow, how it operates. Look at this symbol. That's alternating current. It will flow in both directions. It can goes up. We're using different marker. It can goes up or it can goes up or go down. And so now the question wants to test if you understand the flow well. So this is it. Now if you reach this point, it can never go toward this side. It's impossible. Why? Because this is reverse bias. Diode does not flow across if we have this line. It's not possible. So our closest is like this. So if you're going like this, which means the diode must be connected like this. That's the meaning. 1. Just we are doing that, so it's impossible to go this way. Let's continue. Now the current will go like this. Current is like this. This is a junction, but the current must pass through a resistor. You get, before it can't just go through this phase like this. No, it can't. It must pass after, when it comes out from a diode, it must pass through a resistor first. When it passes through a resistor, the voltage will drop here. So the current is going like this. Once it passes through like this, the voltage from here will drop. So before it can now enter somewhere, it's still going like this. Now, note that the current it will never pass the initial part. The current will never go through the initial part. So, which means that from this place, the initial part is up. The initial part is this side. So this is where it will go through. If current is coming through here, which means the diode is like this. Yes. It will never go through the initial part. It will never. So it go through another part and a lower potential. That initial part already is at higher potential. Now, like I said, current can also go through the lower to the other side of the AC. This, of course, you know that here is impossible. It won't go through this direction because it's reverse bias. So it only go through this direction. So which means that the other diode is there. The other diode is there. to go, like I said, must go through the resistor. So which means in both directions, current go through this space. So this one will go up like this. It won't go through the initial part, it will go through the next part. That's it. So that's it. In both situations, the current will pass through the same direction across the resistance. It should be the same direction. Take note of that. That's done. We've completed the figure. On figure 7.1, go an arrow to indicate the direction of current. Oh, this is it. We've done that. Look at direction of current. This direction of current, both red and black, the same direction. Now, the next one is a graph. Voltage in is plotted against period as shown, as you can see it. So, all the questions. It says sketch the variation of B out. This is sketch B out, the output voltage. Now the essence of rectification is to convert AC to DC, and it's always like this. If AC is like this, DC would be like this in one direction. Now the voltage in here, look at it now. This is AC. The V in is AC in rectification. The V out will be DC. So in DC, we don't need the one that cut across the x-axis. It must not cut across the x-axis. So all you need is this. You just flip this one. Let me use another pen. You just flip this one. Flip it. This one is as pass. It has not crossed. The one that crossed the x-axis, just flip it. That's it. So at the end of the day, so let's see the first one from V0 to this point. What's the line? 1, 2, 3, 4, 5. V0 to 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Is there a line from V0 to that point? The one we flipped now, from that point to 1, it has the peak at 0.5. Please check it. 0.5 t. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. From this point to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think somewhere here. Let me check it again. 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. Is there? Let's flip it. That's the one I flipped before. I'll stop here. The peak is at 0.5. That must sketch it at the peak. The other one is also 10, but the peak is 1.0 t. This is the peak. 1, 2, this is 5, 6, 7, 8, 9, 10. To stop here. Start here. This is the peak. The peak of this one is here, 10 line. Is 5, 6, 7, 8, 9, 10. Something like this. Come back here. And the last one, yeah, from that to, so this is it. This is a DC. Yeah, This is graph. This is graph of output. It must not cut across the x-axis because it's a direct current. Converted it. The next question. The power dissipated in the resistor is P. Sketch the variation of P. Okay. The variation of P. The power and the voltage, we have the same graph. Yes. The power and the voltage. Power is equal to IV. Power is V squared over R. So power and voltage. Whatever voltage you apply, you get the equivalent of the power. So it's the same thing. The graph of voltage against period and the graph of power against period will be the same. So it's like the one I sketched earlier. 1, 2, 3, 4, 5. Start from here to here. This is a peak. This is a peak. This is a peak. So 1, 5, 6, 7, 8, 9, 10. So the same. 6, 7, 8, 9, 10. The same. 6, 7, 8, 9, 10. The same. And this. They are the same graph, the power and voltage. This is it. Now the next question. Suggest with a reason how the root mean square value of output compare with the root mean square value of in. Okay. Okay, this is it. What I can see is that we have the same power, time, graph. We have the same. So just reason how the root mean square value of V out compare with the same power time graph, the same power time graph with V in, time, graph. That's let me check it properly again. The same power time graph. Oh, with yes, with. Okay, I just noticed something. With or without rectification. Do you know? Oh, okay. Let me quickly show you something. You know, root mean square current is peak current over root 2. Root mean square voltage is also what peak voltage over root 2. And you know that power is root mean square current times root mean square voltage. So yes, with or without rectification, we are going to have the same power times that, either rectification or not, because the peak current or peak voltage does not change. Number 8. Let me change my this. Number 8. Now figure 8.1 shows the lowest 4 energy levels of an electron in an isolated atom. Shows the lowest 4 energy level of an electron in an isolated atom. Now, we've seen for the lowest 4 energy level of an electron. This is it. In an isolated atom. Figure 8.1. Figure 8.1. Okay. Show the line in the emission. Okay. 8.1 show the line in the emission. Okay. In the atom that corresponds to the transition of electron from 3 to 1 and 4 to 1. 3 to 1. Okay, emission. If they emit, they will fall. from 3 to 1 and 4 to 1. Three to 1 and 4 to 1. Now explain with reference to photons why there is a single frequency of electromagnetic radiation that corresponds to each transition. Okay, first let's do this. Let me get the energy level since we are not given. Let's get the energy, the magnitude or energy level for each transition. Let's get the energy level for each transition. Let's get the energy level for each transition. Now, using this En minus 13.6 eV, it makes the work easier since we are not assigned any value. This is allowed. This general formula. So for E1, for the first one when n is 1, you can get it like this, 1 squared. So this will be minus 13.6 eV. E2 when n is 2, that's divided by 4. 13.6 divided by 4, that's 3.4. This will give us 3.4 eV. E3 when n is 3, 13.6 divided by 9, as E3 give us minus 1.51 eV. E4 when n is 4, minus 13.6 eV divided by 16. 13.6 divided by 16, that gives us 0.85. This gives us minus 0.85 eV. Now, I hope that the work will be kind of easier. Now, first, let me do n from n to 3. Let me start from the beginning, n to 2 to n to 1. What's the change in energy level from 2 to 1? That's E2 minus E1. What's E2? Minus 3.4. E1, that's minus 13.6 eV. It gives us that. So 13.6 minus 3.4. So the change in energy level there is 10.2 eV. From 3 to 1, when n is 3 to when n is 1, the change will be E3 minus E1. E3 is minus 1.51 minus 13.6. So 13.6 minus 1.51, we have 12.09. The change in energy level there is 12.09. Let me also do when n is 4 to n is 1. The change in energy level there will be E4 minus E1, which is plus E4 minus 0.85 minus that, so 13.6. So 13.6 minus 0.85. we have 12.75 eV. So what do you notice there? Now, what we notice there is that at what you notice that difference of energy level, give us a single photons, and this 10.2 is unique to a particular frequency. This 12.09 is also unique or discrete to a particular frequency. The difference in energy level gives us a single photons of energy, which is unique or which corresponds to a particular frequency. So now, the question they ask us, and don't forget that energy is equal to HF. So energy is proportional to frequency, or energy is Hc over lambda, which is energy is inversely proportional to wavelength. Now I can now write this. Difference of two energy level. Difference of two energy level is equal to energy of a single photon. Is equal to energy of a single photon, because energy level and photon are discrete. They are unique, they are discrete in value. Hence, each difference is difference in energy each difference in energy correspond to a unique each difference in energy correspond to frequency of radiation. I mean, is unique like this. Each difference in energy level, like I said here, single photon, because energy level and photons are discrete in value. Hence, each difference in energy level or in energy correspond to a frequency of radiation. Yeah, let me use A, correspond to a frequency of radiation. So I think you get this is what I'm trying to talk about. So they are unique each. So you can't get the same value of energy level for different levels. Each difference in energy level correspond to a particular single photon, which is unique, which has its own frequency of radiation. That's just what I'm trying to say. The next one, on figure 8.2, draw a line that corresponds to transition N to 2 and label it A. 3 to 2, label it B. We should do it on figure 8.2, okay? Now, this figure 8.1. Figure 8.2. Okay. Draw a line from that corresponds to transition of 2 to 1 and 3 to 2. Okay. 2 to 1 is A. I think I've done 2 to 1. 2 to 1, this is 2 to 1, A. It gave us 10.2 EV. The next one is 3 to 2. Where's 3 to 2? I've even done 3 to 2. Let me do it here. So 3 to 2, that's when n is 3 to when n is 2. The change in energy level will be E3 minus E2. What's E3? From here, E3 is minus 1.51 minus 1.51 minus that E2. E2 gives us what is it? 3.41. 3.41. So 3.41 minus 1.51. That's 1.9. So change in energy level, we said we should label it B, is 1.9. Here, like I said, I said energy is inversely proportional to wavelength, and also energy is directly proportional to frequency. Now, EA, I think EA gave us the one for A, that's 2 to 1. It gave us 10.2. Gave us 10.2. The one for B gave us 1.9. EA is higher than EA is 2 to 1. Is higher than EB. So which means it will have EA it has high energy. The wavelength will be low. This one has low energy. The wavelength will be high. And at the same time, the wavelength will be high. At the same time, this one frequency will be high. The frequency for EA will be high. The frequency of this one will be low. We have high frequency for A, low frequency for B. But the distance, okay, so let's look at it like this. Let's go there. You said we should draw it here. Increasing frequency. If it's increasing frequency, EA, increasing means starting from the lowest to highest. Which one has high frequency? FA has high frequency. So FA will be here. With somewhere, A will be here. Then B will be before A. So it's increasing frequency. And like I said, from 2 to 1 and 3 to 2. So now A, if you check A will have low wavelength, B have high wavelength. So A will be very close, okay, to the pair. Okay, let me put it like this. A should be closer because the wavelength will be low. So this is A. This is A. Because the wavelength is low. And this is B. B will be a bit further apart from the pair. This is what they are asking us to do. Okay, the next question. The frequency that represent line A is FA. Line A, if you remember, I think it's from 3 to 2. Let's check it. Yes. No, B is 3 to 2, A is 2 to 1. A is n equal to 3 to 2. So that will be E3 minus E2, which is equal to HF. In this case, the frequency F of B. f of b. For a is fa, right? From 3 to 2. Okay, let me put it properly. Okay, let me even put it again. A and B. Let me check the transition properly. A is 2 to 1. A is 2 to 1. If A is 2 to 1, from n equal to 2 to n equal to 1, that will be change in energy is E2 minus E1. The change in energy is equal to HF. And in this case, we are looking for A, equation 1. B is from n equal to 3 to n equal to 2. Change in energy for B is E3 minus E2. So for B, we have E3 minus E2 equal to HFB. I call it equation 2. So determine the expression for FA and FB E1 in terms of FA, FB, E1 and the Planck constant for energy level E3. We are looking for E3. So since I'm looking for E3, so add equation 1 and equation 2, add it together. That will be E2 minus E1 plus E3 minus E2 equal to HFA plus HFB. So I'm looking for E3, right? From here, E2 cancel E2. Add here is what? Minus E1 plus what? E3 equal to H into bracket FA plus FB. So I'm looking for E3. So E3 will be HFA plus FB plus E1. That's what they are supposed to do. So E3 is H into bracket FA plus FB plus E1. That's it. Number 9, we are asked to define mass defect. You have to define mass defect. I spent 2 hours, quite long. Okay, this one is quite simple. Mass defect. Okay, let me put it like this. This is equal to the difference. This is equal to the difference between the total mass of the individual separate mass of the nucleon, and mass of the nucleus, So, okay. Okay. The next one, the nuclear fusion in a particular star is described by this, where X is a particle that has no mass. Okay, it has no mass, it's massless. State the name of X. Okay, I don't know what is on top, that's the mass number. What is down, that's the atomic number. So the whole idea is the total top to the left must equal to total top to the right. So A is 1. Total bottom to the left must equal to bottom to the right. B is 0. So X is 1, 0. That's Newton. That's it. That's Newton. That's it like that. The next one, if you are given equation and you have to show that energy release. Okay. What's energy? MC squared. So energy is MC squared. The M is the mass defect. The M is the mass defect. And what is mass defect? In this, from this equation, it will be mass of the product minus mass of the reactant. This is the product. In this case, the product is only helium because neutron is massless, and this is the reactant. That is the isotopes of hydrogen, tritium and deuterium. This is the reactant, and this is the product. So mass defect would be what the mass of the product. Now, here the product here is this. They've given us mass defect in U. So mass of the product is 0.030377 U minus the reactant, the 2 deuterium. Look at it, 0. This and this. That's the reactant. That's 0.002388 plus 0.009105. So when you do your maths, a mass defect, the mass defect is 0.018884 atomic mass unit. When you check the MF19, this is 0. Oh, sorry, no MF19. Math is MF19. When you check the front page, 1 atomic mass unit is 1.66 or 67 times 10 per minus 27. So we can now get the energy. Now, remember that energy is mass defect multiplied by speed of light. So the mass defect is 0.018884 times 1.66 times 10 to the minus 27. See the speed of light 3 times 10 to the power 8 all square. Now the energy will be 2.8 times 10 to the power minus 12 joule. That's what they asked us to show. I guess 2.8 times 10 to the minus 12 joule. Now question C. Now question C is almost done. The star in B has this radius 2.3 times 10 to the power 9 meter. This is the radius. This has the luminosity L. These are luminosity. I think there are fusing astrophysics to this. All the energy released from the formation of helium has radiated away from the star. All the energy that is radiated from the star have been in the formation of helium. Yeah. Determine the mass of helium produced per unit time. The mass of helium produced per unit time. Okay, remember that power is energy over time. But in this case, power can also be the amount of energy released per unit time. From here, amount of energy per unit time is power over E. So the amount of energy released by unit time. What's power? From the question is 1.4 times 10 to the power 28. It's measured in watts. It's also the luminosity. Energy, the one we just got now, 2.8 times 10 to the power minus 12. The amount per unit time is 5 times 10 to the power 39. Per unit time is per second. Now, the unit giving us is kilogram per second. Okay. Now, what is mass per unit time? Mass per unit time is something like mass times 1 over T. And what is mass? What's our mass? I think our mass is, let me check it. Let me check it. What's our mass? We are talking about helium. The mass is 4 atomic mass units. And this is, this should be in kilogram. So this one is per second. And what we get per second is 5 times 10 to the power 39. So it makes sense with this unit. And 4 atomic mass unit. 1 atomic mass is 1.66 times 10 to the power minus 27. Multiplied by the per second, which is 5 times 10 to the power 39. So it gives us 3.3 times 10 to the power 13 kilogram. We have another method to do it, but probably when I'm done, I'm just probably in one of my topical videos, I'll show you some short approach of it. So this is also short enough. Now, surface temperature of the star. Luminosity, the formula is 4 pi Stefan Boltzmann constant R squared T raised to the power 4. We are looking for the temperature. So temperature will be luminosity over 4 pi this R squared. So what's luminosity? 1.4 times 10 to the power 28 over 4 pi. Stefan Boltzmann constant is on the front page, 5.67 times 10 to the power 8. The radius, that's one of the first thing I pointed when I was reading this question. Okay, you can see the radius, 2.3 times 10 to the power 9. 2.3 times 10 to the power 9. So do your math, find the fourth root. So find the fourth root of this. So at the end of the day, temperature will be fourth root of that. So I think you're going to have 7.84 times 10 to the power 3. So which it can be 7,800. Okay, that's the question. I think we have one more question. It's been a long day, 2 hours plus. I think this is the last question. Let me check it. Oh, fantastic. This is the last question. X-rays for use in medical diagnosis are produced in the X-ray tube. The X-ray tube charge particles are accelerated towards the metal. Charge particle, probably electron. That's electron anyway. Toward the metal target. Metal target is the anode, and the metal target is an atom. By an applied potential difference. Okay, what accelerated electrons are? PD. If you remember this, V equal to work done over charge. Work done is QV. This is what accelerated. This is what they are talking about in that part. So state the name of the charged particle that are accelerated by electron but accelerated by PD. Okay, the charged particle is electron or electrons, not one. Explain how X-rays are produced. You guys are going to enjoy my topical section that details. Let me quickly summarize what they asked us. It's 2 marks, so I'm not supposed to go deep. This is a process. High-speed electrons. High-speed electrons. High-speed electrons are being high-speed electrons are being bombarded. Towards the heavy nucleus target. Toward the heavy nucleus target. Like I said, the target is an anode, an atom. So once this happens, toward the heavy metal target, which slow down or decelerate. Let me put it like this. This slow down or lead this slow down or high-speed electrons are being bombarded toward the heavy nucleus target anode, which slow down or lead to the deceleration of the electron. Slow down or lead to the deceleration of the electrons. Full stop. Kinetic energy is lost. Kinetic energy is lost due to the deceleration. Okay, now. Kinetic energy. Okay, this. Kinetic energy is lost or emitted in form of X-ray photon. This is how X-ray produced. The loss in kinetic energy, where it's going to, is the one that converts to X-ray photon. That's it. Calculate the minimum wavelength of X-ray produced when this. Now, remember I said the work done is QB. Work done is energy, which is QB EB. E is equal to hc over lambda. So minimum, here will be maximum. What we are looking for is what? Minimum wavelength. So minimum wavelength will be hc over EB maximum. So the minimum wavelength, h is 6.62, I guess, times 10 to the power minus 34. Speed of light, c, 3 times 10 to the power 8. E is 1.6 times 10 to the power minus 19. Voltage 5.8 kilovolt, 5.8 times 10 to the power 3. So use a calc, punch it 2.14 times 10 to the power minus 10. So the minimum wavelength is 2.14 times 10 to the power minus 10. The next one. X-ray pass through a medium that has an attenuation coefficient of 1.4 per centimeter. calculate the percentage of X-ray absorbed by a thickness X of 2.8. So attenuation is I naught, intensity transmitted equal to I naught minus this. The percentage of the ratio of transmitted over the original, which is this. So ratio of transmitted over original, the thickness is 2.8. The coefficient mu is 1.4. It is per centimeter. I need of converting. Multiply by 2.8. IT over I naught will give us e raised to power this times this. Everything give us 0.020. They said the percentage multiplied by 100. No. We're not there. So give us that percentage absorbed. This is IT over what? I naught. So the percentage absorbed. So the one that is transmitted, the percentage that is transmitted is this time this will give us 2%. So the one that is absorbed will 100 minus 2. That's 98%. The one that is absorbed is 98%. This is transmitted, this one is absorbed. Okay. See you guys. Please subscribe to my YouTube channel. If you gain anything reasonable enough, please share it. Don't be selfish. There are many of my content coming on your screen soon. I remain Dr. Ajani Ahmed.